Yeah, I know. It's not biological correct. You're actually the first one in the audience to notice it. In the previous talk, nobody noticed, but that was at the World Wide Web conference. Tells you something about the audience. Okay, so now, let me just some paper. Okay, so directed graphical models. We've actually done some of that already, and let's just start with something very simple. It's almost simpler than what we have before. So we have some web server, right? And it manifests itself on a website. And in order to make it run, I need a database and I need a web server. And if both of them are behaving properly, then the site's up. If they're not, then, well, somebody's in trouble. So a rather crude model would be that I model the joint distribution over MySQL, Apache, and the website as P of W, website, given the database and the web server, times distribution for the database and the distribution for the web server. Now that's of course not quite so accurate, right? Because suppose I get a denial of service attack on the website, then maybe the database is going to get in trouble, right? If I get too many requests, or somebody might go and hack the server. So this is a model, and it's not necessarily accurate, but it's an okay model. Okay. So what happens, however, is before that we could assume that essentially the behavior of the database and the web server are independent of each other. However, as soon as I go and observe the website, they stop being independent of each other. So here's what happens. P of M and A given W is just, this expression here. And now I need to normalize. And I normalize by basically summing this expression here over all M prime and A prime pairs. And this now clearly does not factorize into expressions containing only M or expressions containing only A. The denominator is fine. That doesn't really contain any M and A. But the numerator couples through this joint term here. So what happens is that all of a sudden, conditioned on observing the website, A and M become dependent on each other. So this, if you think about it, there's actually something very subtle going on. We had independent random variables before. There's no really causal connection between them. They are both serving as inputs to something else. But as soon as I observe that other thing, the constituents that built this thing now become dependent on each other. So it's really important that when you design a graphical model that you check such things, because it's so easy to get it wrong. So especially when you do the modeling, make sure you get all those effects right. So here's a practical example of what's going on. So if the site is working, I know that the database and the web server are working. So I can immediately infer those two things, so they're clearly not independent. Now, if it's broken, I know that at least one of the two services has to be broken. I don't necessarily know which one. It could be both of them. But their distribution, again, isn't independent anymore. For instance, if I know this site is broken and I also know that the web server is actually working, I know it must be in the database. So mind you, this is all a very, very simplistic abstraction. It doesn't really work that way in reality, but this is just to motivate a little bit how things depend. And I didn't want to drag out the burglar alarm in the earthquake again. So here's why you would actually care about doing this, right? So you get a lot easier estimation. So suppose I have a model in those 4 random variables, right? Database, web server, website, and the user. Then if I wanted to do parameter estimation in this model, I would really need, if I want to get the full joint distribution, I would need 15 parameters. Right? That's actually a lot of parameters for this simple model. But if I exploit this factorization assumption, well, I need 6 parameters. Now, 15 versus 6 isn't such a drastic difference yet, but I can get cases where I need linear rather than quadratic numbers of parameters if I make certain simplifying assumptions. On top of that, I get causal relations. I can ask, well, you know, what would happen if I were to turn off the web server? On top of that, I can actually do inference for all the unobserved variables. So for instance, if I stand in front of, you know, a server cabinet and I know certain lights are flashing, I can probably do some inference as to what the machines running in the backend are doing. So does anybody have an idea how I get this 1 plus 1 plus 3 plus 1? Well, let's have a look. So 1 comes from here, right? So I need the probability that MySQL is, that the database is running. I need the probability that the web server is running. Now, for the website itself, well, basically I need its behavior conditioned on all 4 possible outcomes that these 2 variables can have. And since they all need to, so I get this. And then in the end, the user behavior will depend just on whether the website's up. As a matter of fact, that's not quite accurate. It should be a 4 here, right? Because basically for all 4 possible configurations, I need to know what the website does. Now, here's an important thing. So here's our chicken, not very anatomically correct, but prettier. And here's the egg. And so what happens? Chicken lays the egg, but the chicken hatches from the egg, right? And so there's this century old philosopher's dilemma: who came first, the chicken or the egg? And in graphical model speak, that's like writing out something like that: P of chicken given egg times P of egg given chicken. That's not the proper probability distribution. What would be valid is either to ask, well, P of chicken given egg times P of egg, or P of egg given chicken times P of chicken. And so this is a no-no. Here's actually, okay, does somebody have an idea how we can resolve this? Yeah, we can cook a dish with chicken and egg, and that's the end of it, but does anybody have an idea what's wrong with this model? Okay, what's really wrong with it is that we completely ignore the temporal dependence. Because it's not the same chicken that hatches from the egg that laid the egg, right? So we have a time axis on top of that. And with that time axis added, all of a sudden it actually becomes a simple Markov chain, and we can do inference in it. And we can have exactly this causal relationship of chicken on egg, right? And all is fine. It's just that we collapsed one random variable that shouldn't be collapsed. And then you get this mess. So it's very simple, but you know, shows you, I know this is like a trivial example, but it shows you a little bit, you know, what things you need to watch out for in terms of modeling. So usually when you get loops in your reasoning or in your graph, you may have overlooked another variable that disentangles this. So for instance, imagine that I want to go to, you know, a concert, and a friend of mine also wants to go there, and then he will go if another friend of mine goes, and so on. So I get the circular dependence. Then, you know, you actually get the problem of, you know, who now influences whom in what way. And if you put the time axis on it, you might actually get the decent graphical model. Otherwise, at least a directed graphical model is not going to do it. There are other models which work for this, undirected ones, and we might get to that tomorrow or probably on Wednesday. Okay, so here's the general beast. I have a joint probability distribution over those random variables, And I'm writing it in such a way that I say, well, P of x is given by the product of P of xi given the parents of I. So if you look at this graph, you will see that there's no loop. I can have some variables influencing that variable in multiple ways. So I could have, for instance, I go here or I go directly. That can happen. But you must never be able to go around in a circle, nowhere in the graph. So if I have a directed acyclic graph, I'm in good shape. And the nice thing is that if actually observe all the random variables, then log of P of x given theta is just the sum over log of P of xi given the parents of I. And this is really easy to solve. So it's a simple, efficient optimization procedure. It's nice and convex. Sometimes I can integrate out, so all is good. Let's just, if we don't observe everything, that's when the fun starts, and I'll show you a little bit how to do it. Let's first look at chains. As I want to show you a little bit the vocabulary of graphical models that goes with it. So I might have a Markov chain, like the past influences the present, which influences the future. Now, again, this looks like an awfully repetitive structure, so I'll write a for loop. It's the for loop. So I have a plate which says, well, repeat. The only difference to what we had before is that we now had arrows that go through that plate, inside and out, and they are understood to mean, well, it references to the previous guy. Sometimes you would actually make a copy of this variable here, and you just identify it by having the same name. Yes?
So how do you distinguish like a single variable coming in versus like 10 coming in and 10 going out?
Well, if I had 10 coming in and 10 going out, then I would actually need to make, well, 10 copies in here, right? Or if I wanted to have a loop over 10, I would have a second plate inside, which would just say repeat 10 times. And so that's exactly a nested for loop. Very good question. Thanks. Now let's look at a hidden Markov chain. Well, for instance, you might have a website, and we show search results, and we don't quite know whether the user is actually looking at them. The only thing that we observe is whether the user clicks. Or, I might actually, have a computer game, and what I observe is only how the user interacts with it, but I don't really know what's going on in the user's mind, whether he's really engaged and happy and whatever. So here's the corresponding plate. So now we have two guys. This one here doesn't have any arrows pointing outside. This one is the unobserved variable. And I've just introduced another piece of notation, namely, well, unfilled plates, unfilled nodes usually mean that I'm not observing the random variable. So that's sort of a standard notation that if I have a shaded node, I observe it. If it's unshaded, it's unobserved. Okay. So now that we have the pictures, let's use the equations. So here's what we get. P of x parameterized by theta is, well, you have to start from somewhere, P of x naught given theta, times the product I going from 1 to n minus 1, P of xi plus 1 given xi and theta. Right? So what I need is exactly this. Okay, I have to start from somewhere, and then you just repeat accordingly. For a hidden Markov model, well, again, you start from somewhere. You have the Markov chain, so this is exactly the same object as what we had here. Right? And then I need to deal with the emissions. So I need to deal with P of yi given xi. And quite often what happens is, yes, I observe some things, but I don't quite know what's going on inside the system. Okay. Let me show you a few more models. Factor graphs, for instance. So I might have some latent factors and have observed effects. So what are the observed effects? Like click behavior, queries, watched news, emails, whatever. Latent factors would be user profiles, news, content, which keywords, who I'm connected to, basically just any attributes that I can't measure directly. Or that might be too expensive to measure directly. So for instance, in many cases, I could actually go and pay an editor to look at a user session, to analyze it, and to come up with a best guess. And then I could even pretend that this best guess is the truth, which is probably really far from the truth. But if you don't want to do graphical models building, you can actually pay editors a lot of money and basically replace good algorithms by a lot of money. And yeah, a lot of early web approaches do that because the engineers say, well, we want to build a model. By the way, I've heard there's this classification algorithm, so we don't know all the other attributes, so let's just pay editors to generate them for us. Then we'll learn it, and then we'll be fine. And a lot of companies on the internet currently do this. But this is, I believe, where things ought to be going. Recommender systems. So you probably heard of this, right? So we have users and movings, and we have ratings. And by the way, here we have exactly those for loops that are interlocking. So there's a loop over all the users. We instantiate all the movies as well. And then what I have is that not for all user-movie combinations I actually observe the ratings. And yeah. Now where does this occur? It occurs in news, SearchMonkey, Answers, social, any ranking, personals, and so on. Or for instance, some what's new and hot systems. So you get actually a fair number of challenges. One of them is, well, how do we design the models in terms of engineering? What dependency makes sense, and which part is computationally tractable. And that first part is often ignored in the machine learning literature, and among the engineers, they don't even think about computational tractability often in the end. In the sense that, well, they just pick a very simple model and are not daring enough. And so I hope that after this lecture and a few others, you'll go back to, whatever jobs you may have, or maybe when you take up a job and you encounter such problems, really think of both aspects. The domain knowledge is amazingly valuable. So the worst thing you can do is you can't just come in and say, well, look, guys, what you're doing is all nonsense. I have a better model. Usually, there is a lot of fine-tuning and engineering that went into the current design of a system. Well, sometimes it's also quite obvious that it hasn't, but that's a different story. And try to recover as much as you can from that. There's a couple of things that I'm not going to discuss in this class, which is basically all the dependency analysis for directed graphical models. There's the so-called baseball algorithm by Schachter. And you can read up on that. It's actually a very pretty algorithm which shows you which things are dependent. And what I'll be talking about a bit is how to do inference. So dynamic programming, message passing, and so on. Any questions right now? Okay. Now I need you to pay attention because it's going to get technical. Dynamic programming. It's not hard. It's actually fairly straightforward. You just actually need to, pay attention and look at it carefully. So let's take a simple chain, write P of x parameterized by theta. It's just that product. So we can just write it out. And I can ask a question, what's the probability of xi? The ith element in the chain. But of course, that depends on all of its neighbors that came before and all of the things that come later. And so if I write it out, it's just, the sum over all the x's except for the xi. And then this monster here. If I have a binary sequence, and the sequence is, maybe 100 bits long, 101 bit long, right? Then you would already have to sum over a space that has a size of about 10 to the 30. So any naive approach to that is completely futile. But what we can do is, let's just do the following redefinition, right? I'm just defining p of x naught to be some function L naught of x naught. Okay, nothing has really happened yet. Now look what I'm doing. I'm pushing the sum over x naught inside. Perfectly fine, so the rest of the sum starts from x1. I'm pulling out the p of x1 given x naught. So I'm basically pulling out that dependence here. And lo and behold, I can actually compute the sum right away here in closed form. Why? Because this is the only other term that depends on x naught. I know that by looking at this graph. And then here I have a product that starts from 2. Nice. Can we do that again? Yeah. Now I push the sum over x1 inside. I have L1, which is now this sum here of x1, times some function that depends on x1 and x2, times the product which starts at 3, and so on. So I can do this entire forwards recursion. I can also start from the end and get exactly the same reasoning here. I'm not going to walk you through the details, but it works exactly the same way. You take the last term, you sum over the last variable, you get something that only depends on the second last one. You then, take care of the sum of the second last variable, you get something that depends only on the third last one, and so on and so on. And so that's how you work your way from the end to that variable here. So now what we have is basically we've managed to compute the sum over everything up to variable I from the left and everything from the right. And these are factors. Then I just multiply everything together and I'm done. This is the simplest version of dynamic programming message passing. Does anybody have questions about this? Because we're going to generalize this now. Okay. So the reason why it worked is we basically successively peeled off one variable after the other. And that one variable was connected to the rest through only one more variable. So we managed to remove the first variable and got something that depended only on the second one. We then peel off everything that couples the second and the third, get something that depends on the second variable. And they keep on moving forward. They do the same thing at the end. Okay. If you've never done this before, a good idea is to try and solve a linear system of equations of the following form. So if I have something of the form AX equals Y, where this matrix A has the following shape. It's a diagonal matrix. And then I have something on, let's say, the upper diagonal. I could also have something on the lower diagonal if I wanted to, but to keep things easier.
Just for the whole triangle.
Yes. But if I had a triangle, the algorithm would be a lot more expensive. If I have something that's just banded diagonal as I drew it, I can solve that in order n time. And the reason why I can do this is because I will have basically an equation of the form. Let me just write it out. So I'll have A11 x1 plus A12 x2 equals y1. So I can solve for x1, right? It's just, well, basically A12 x2 divided by A11. So I get this minus plus y1 to A11. I then plug this into the equation where then I solve for x2 and I keep on going through, and this way I can work my way through all the variables. This is the equivalent of message passing for graphical models, for matrices. And as a matter of fact, if I have a Gaussian graphical model, I will end up doing exactly those operations. It's the connection between message passing and sparse linear algebra. If you've never seen this thing before, now's a good time to ponder and learn about it. Okay. So let me show you the forward recursion in general. So here's what we have. We have L naught is P of x naught. Li of xi is just, the previous variable that we had times then, a joint potential. Backwards, you do the same thing. You get P of xi is just Li of xi times Ri of xi. And, well, I can get also things like this conditioning. And if I want to have two variables, well, you just stop the recursion one earlier. Now, let's just write this in terms of message passing. So I'm sending a message forward. The message going from the left to the right, so from I minus 1 to I, is just what I got with the previous message times some coupling function. Likewise, the message going from the right. So this doesn't change algorithmically at all. I've just rewritten things. The reason why I've rewritten things is because we now can use this for trees. Suppose I had the following dependence. Some variables depend on each other, all of a sudden it branches off. So for instance, it might rain. Whether it rains might affect, how wet I get when I come here, which might affect whether I can actually start my lecture or need to get changed. Now, depending on whether I start my lecture, this will affect whether the video recording will be working, and it might affect whether you fall asleep during the lecture. Right? So these are two different chains, and it's quite conceivable that whether the video camera is on or not might not affect your sleeping pattern. So in that case, if I, for instance, want to go from variable 2 to variable 3, I need to incorporate all the messages coming in from x1, but I also need to look at how x6 is behaving. So I need to incorporate the message going from 6 to 2, from 1 to 2, and the coupling function that couples x2 and x3. Likewise, the message going from 2 to 6 needs to incorporate this and that in order to send here. So the only difference is now that if I have a vertex that has more than one neighbor, I need to incorporate the messages from all the other points.
That's regardless of the direction.
Yes. So this is actually an extremely important observation that you just made, that it's regardless of the direction. I mean, the algebraic form of these functions f depend on the direction, but for inference, the direction doesn't matter. And that important insight is going to help us afterwards when we do undirected graphical models, because we will be using the identical inference algorithms for directed and undirected ones. There's no difference whatsoever when it actually comes to inference in a Markov chain with errors or without. And there's a beautiful paper that belabors that point in quite a bit of detail. It's by Frey, Lerliger, and Xishang, I think he's the third author, or maybe the first one. But it's basically called factor graphs. It appeared in IEEE Information Theory. A year before that, there was this paper on the generalized distributive law. Those two papers did a lot to clarify these connections. And I'll get to the factor graphs and the generalized distributive law in a moment by showing you that this doesn't only work for the sum product algorithm that I showed you before. Remember, here we have sums and there are products, but also for plus, log plus, the Boolean semi-ring, and min and plus and max and plus. So I'll show you that in a moment. So here's what happens with the messages if we want to actually do the computation throughout. We start from the leaves. We send the messages here, right? Now that the two messages that I need to send a message on here have arrived, I can create an outgoing message there, and I send it on. Right. for any message that should have gone in this direction, I would have had to start here and there and send it back. So that's the message passing algorithm. Okay. Now, actually, it turns out that this is a little bit more general than what we initially thought. There's something called junction trees. Let's just start with the click potential. Remember here we had this operation, right? So we have message going out from I to j is the sum over the variables on this vertex times all the incoming messages but the one that goes out. Okay. Now I can do the very same thing here. And the only difference is that now here I've said, well, actually this first function here depends on variables 1 and 2. This depends on variables 2, 4, and 5. This one on 4, 5, 7, and this one on 2, 3, 4. What this means is that now the message going from this set to that set, the variables that they have in common is variable number 2. The variables between this set and that set are actually variables 2 and 4. So I have to send out a message that involves both of those guys. Likewise here. So what you get is you go from a tree to a so-called junction tree. Junction tree, the easiest way to imagine it is basically like a tree with highways as connections, right? So you can have more than one edge. And that, yeah. Now, the interesting thing is, what do the messages need to contain? Basically, the state of what's called a separator set. Separator set is the intersection of the sets of variables between two vertices. So in our chain before, we had between here and there, the common variables were 1 and 2. Here they were 2 and 4. There were 2 and 3. So these are the variables that we needed to share. Junction trees, it's just more general. There's nothing else to that. If you understand this, you basically understand message passing in graphical models, and you can write nice papers and implement things.
Can you write them automatically?
Yes. As a matter of fact, you can. Good place to start looking for that is GraphLab. Probably in 3 months, it will be available for Hadoop. Right now, you can get the multi-machine version as it is from CMU. If you want to work on single machine, but with general semi-rings, you can download Julian Macaulay's Python library, which does exactly that. It's not as fast, but very general. Okay, so let's just look at junction trees again. Here we have the click potential. We send the message through, and we send it out. There we go. Okay. Now, let's go to the generalized distributive law. So remember what we had is we had those sums and multiplications, and maybe we can replace them with equivalent operations from other semi-rings. The semi-ring is basically a set of operations and symbols that admit an addition and a summation. So you need the following two laws. You need the associative law, which means basically A plus B plus C. I can just switch the brackets around. And you need the distributive law, and that's basically just A times B plus C is AB plus AC. As long as I have a set of symbols which allow for that, I'm in good shape. Can somebody think of such a set of symbols? Anything else than plus and times? Can you speak up?
Or and and.
Pardon? Or and and. Yes. Perfect. Very good. That's the Boolean semi-ring. Anybody else? Union and intersect. Perfect. Great. Yes? Yeah, that would probably work. Yeah, pushing everything to the XP. Yes? Very good. hadn't thought of that. Anybody else? Well, you can do the opposite of exponentiation, right? You can take the standard plus times semi-ring and take the log of it. And you get plus and log plus. Actually, log plus and plus. So here are a few examples. So remember, the distributive law goes like A times B plus C is AB plus AC. Now this is a really important one, the max plus and likewise min plus. So it's called the tropical semi-ring because it was invented supposedly in the tropics. Supposedly in Brazil. That's why it's called tropical semi-ring. And if you hear somebody talk about tropical geometry, they mean doing geometry-like operations with this kind of semi-ring. So it sounds more exotic than it actually is, I would say. So max plus, let me show you. So max takes the role of sum, and plus takes the role of a product. So now what I get is A plus, so that's times max of B and C is max of A plus B and A plus C. Right? That's easy. Union intersection, we had that before. Boolean semi-ring and or. And log plus and plus. The exponentiation, hadn't thought of that. That's a very good thought. And then, interestingly, not just max, but also min works. You can see that, for instance, by just multiplying all those numbers by -1, and the relation still holds. And then you realize that the min of minus A and minus B is the same thing as the max of A and B. And that switch goes through the minus the min of minus of A and minus B, of course. Okay, so let's just look at what happens in practice. Let's just do the simple chain. So one thing that I might, for instance, want to do is I might want to find the most likely sequence through, in a Markov model. Okay, so I need to do the max over all x. Actually, I want to get the argmax over these guys. So again, I pull out the first guy, define that to be L naught of x naught. I now have some coupling functions here. And just like before, what I did with the sum, I pull the max inside, evaluate that first, and I just work my way through the chain. So it's exactly the same algebra. As a matter of fact, I took the LaTeX source for the previous slide, threw it in, replaced sums by products, so products by sums, and so on, and got exactly the max plus semi-ring out of it. So it's formally equivalent. And for junction trees, well, you get the same thing here, right? You have your click potential, and you just work your way through. And it should actually show the next slide. Yeah, it does. So in general, you have those separator sets, and now you again just take maxes and sums where you've before that had sums and multiplications. Okay. Now you might wonder a little bit, why on earth am I so concerned about this entire, junction tree thing, right? After all, I might have some loops, and like a function of that form, s of x1, x2, s of plus s of x2, x3, x3 and x4, x4 and x1. So I could just, do message passing and go around once, and then, I get circular reasoning. So I shouldn't be doing that. Instead, what you can do is you can actually define new potentials that turn things into a junction tree. Let me show you a little bit how to do that in general. So we have those variables. 1, 2, 3, 4. We have a simple ring. I can turn this into something that looks as follows. I have 4. I have actually they all depend, sorry. So I have 1, 4, 3. I have a separator set of 3 and 1. And I have a set of 1, 2, and 3. Okay. Basically what I've done is I've triangulated the graph. There is not necessarily a single solution, and actually finding an optimal triangulation is hard. But it's basically this edge that I've introduced here. And now I can do my message passing. The trouble is that now my set that separates these two parts has actually grown. If before that, for instance, here I had maybe 3 states for 1 and 3 states for 3, then I would have to propagate 9 states through for this. So in other words, it's exponential in the size of the set. In some cases, you can get away with it fairly neatly. So for instance, imagine you had a ring more generally. I'm showing you this because it's actually a rather useful construction. And if you want to do geolocation, then 2 years ago or 3 years ago, you could have still written a paper on it. Okay, let's just suppose this is my ring. I've already introduced one edge. So now I do the following thing. I triangulate the graph as follows. And now I can write it. Let's just number things through 1, 2, 3, 4, 5, 6, 7. Now I basically get the Klieg 1, 2, 3. Then I have here 1, 3, 4. Then I have here 1, 4, 5. Then I have 1, 5, 6. And I have 1, 6, 7. And the separators in between here are exactly these edges, right? It's basically 1, 3. Here it's 1, 4. Here it's 1, 5. And that's 1, 6. So basically the message size is bigger. I need to carry the state of 1 throughout. But I can therefore then do things optimally. There are some other graphs where this is not easily doable anymore. And probably the most famous one would be the Ising model. So in that case, you get that type of structure. Because now, in order to triangulate this, I get the effect that a lot of things will clump together. The only thing I could do is I could basically have almost like, a wavefront moving through this way and just combine all those variables. But that's in general very expensive. Okay, good. Any questions so far about a bit of message passing, clicks, and so on, and dynamic programming? Yes? Okay, very good question. So let me just repeat the question. It was a bit quiet, and I hope I understood you correctly. So the question was, when we do this with a graph, well, we effectively change the graph, so how do the functions change? Well, let me show you that in the case of the ring. So again, we take our we start with a simple ring where we have basically S1, 2, so x1, x2 plus s x2, x3 plus s x3, x4 plus s x4, x1. And that was our graph. 1, 2, 3, 4. Okay, so now let's introduce an edge. Let's say we introduce it here. Now we need to basically aggregate the functions that contain variables 1, 4, and 2. Okay, so that's this one here. 1 and 4. We don't need this because it doesn't actually fit in here, nor this one. And I'm now defining a function, let's call it maybe q of x1, x2, and x4 to be s of x1, x2 plus s of x1, x4. And I define a second function q of x2, x3, x4 to be just s of x2, x3 plus s of x3, x4. Right? And now I know that the separator set between them are exactly those variables x2 and x4. These guys. And so if I wanted to do a joint maximization over all of this, my first message going from, okay, let me just change the pen again. The message going from 1, 2, 4 to 2, 3, 4, which now depends on the variables in the separator set, x2 and x4, would be the max over, well, the one variable that's not needed anymore is x1, right? So x1 of q of x1, x2, and x4. Then, in the next step, I get basically q of x2, x3, x4, and I multiply that with my message, 1, 2, 4, 2, 2, 3, 4 of x2 and x4. Now I need to do the max over, well, basically x2, x3, and x4, and then I'm done. Right. And if I know the argmax of that, I can then plug the corresponding values in here, and I get the argmax for x1. Now, for that simple full variable chain, that's extremely contrived. Once you get the long ring, it's actually quite useful. Basically, if you have a long ring, you carry that one variable through all the way to the end until you're basically back at that variable again. You solve for the max, and then you know what the value of that particular variable is, and you can basically disentangle the rest. That's what happens. So it's very simple. But the first time that you see it, it might actually be, yeah, might take some getting used to. Okay, any questions at the moment? Okay, don't worry, that was probably the hardest bit of the entire class. You've survived it. Yes?
Could you please re-emphasize the intuition behind this?
Okay, the intuition behind this is that, okay, so the intuition is you basically have this iterative variable elimination procedure where you get rid of one variable, given the next, and so on, and you move your way through. Now, in general, if I have, not just a simple tree anymore, but a more general graph, I need to bundle my variables together into a hypergraph such that this hypergraph looks like a tree, but just with more connections. So basically, you take your network and you pull it together in such a way that it looks like a tree with lots of highways. And if necessary, you need to make detours. And that detour is exactly this guy here, so to say. And then, once you have that, you can treat it as if it were just a simple tree, but with more variables. That's called a junction tree. And you perform optimization. So that's really the basic idea to it. There isn't very much conceptually to it once you get over the first issue. I never really remember the dynamic programming equations. I just derive them again from scratch whenever I have to. That's a lot safer, because otherwise there's a very high chance you'll just get them wrong. Yes?
Yeah, it's a bit rusty, but I remember, don't we also need to do something about graph moralization when converting directed to
Yes. Yes. So, okay, so you're already a few steps ahead of me. So moralization basically means, in terms of the dependent structure, that you marry all the parents of a child. So you combine them. But that effectively is what happens in the inference procedure anyway. So I've skipped over a lot of these aspects right now just for the sake of, giving you a streamlined presentation. But yes, moralization is an issue. There is no really straightforward standard procedure how you can get a junction tree. As a matter of fact, finding an optimal junction tree is hard. There are a couple of greedy procedures how you can get something that approximates it. But yeah. Any other questions? Yes? Okay, so let me rephrase the question. I'm not sure I fully understand. So you're asking, is there any other solution for solving inference in large graphs that doesn't involve message passing? Well, rather than junction trees, well, you could just brute force sum over all the variables, but that would be terribly inefficient. You could possibly do just belief propagation. So loopy belief propagation that ignores this, where you just send messages and ignore the fact that the messages might actually come back. And under certain conditions, this approximation will converge to the correct solution. You might sample. So loopy belief propagation is something that people do a lot in practice. For instance, if you're using your cell phone, I don't know whether they by now do use turbo codes. I believe they do. If they do, your cell phone is doing loopy belief propagation. In any case, if you're communicating with a satellite, it's doing exactly that. So it's using an inexact solution. And then there is amazingly sophisticated analysis to prove that this is all very well behaved. It's very beautiful mathematics. So if you look in information theory, you'll find a lot of stuff there.
Question on these lines. So does this calculation involving junction trees suffer from the same problems as belief propagation?
Okay, so belief propagation doesn't really have tractability issues. It has convergence issues.
Yeah.
Okay, so convergence issues in two ways. First of all, you're not guaranteed that it'll converge. Secondly, you're not guaranteed that it'll converge to, the correct solution. The latter is actually what you worry about probably most. Junction trees don't have that issue because they are exact. The problem is that you end up with an exponential blow-up in the set of your random variables. And so you can't really do it in general. There are a couple of other means of getting around it. So there are, for instance, variational approximations, there are sampling methods, and I'll actually show you some of these techniques in what follows. Quite often you may want to use a combination of both. So for instance, what you could do is you can say, well, for certain subparts of the tree, of my graph, I can actually perform message passing, and I end up with possibly a thin junction tree. And then I alternate over various trees that I can embed into this. So this gives you a generalization of the tree embedding of Wilsky, Wainwright. So Mike Collins just recently got a Best Paper Prize with Dan Sontag about this. So these are essentially dual decomposition methods for otherwise intractable optimization problems. It's a very beautiful paper that Mike Collins has in that context. It's actually 2 papers, and I think actually both of them got the Best Paper Prize.
Is it the one with David Sontag?
Yeah, that's what I said. Sorry, not Daniel, David Sontag, yes, you're right. And yeah, so there's plenty of other technology that you can use, but in general you would want to use probably both of them. Or even if you have a sampler, and I'll show you a bit more what the sampler does, but I think we're out of time today. You do not want to use, basically if you can, use a sampler that actually samples from an entire chain rather than each variable separately. Because from a chain you can sample exactly, and so this way you get much faster mixing behavior. So for instance, there's a paper by Nando de Freitas, Firas Hamze, and I forgot a third author, where they do this. And it actually refers back to a paper 10 years before them. And I'm really sorry, but I'm going to butcher the names of, these are 3 Chinese authors with 3 letters to each name. And I'm probably going to get it wrong, but basically it's referred to. No, it's not quite that bad. But yeah, in English it's 3 letters. And yeah, basically look it up in the From Fields to Trees paper of Nando de Freitas, and that'll give you a bit of an idea. So basically you sample from a tree, and then you rotate the tree and you find another embedding tree and you keep on iterating. So this is a bit related to the tree embedding of Wilsky and Wainwright as well. Okay, so I think it's pretty much time, because at 2 o'clock there's the next speaker. I think it's you, Manfred. So I don't want to be eating into your time. And yeah, I'm around until Wednesday, so do ask, and I'm around in the breaks too. Okay, thanks.